Hello, my name is Stefan Nikolovski, and I'll be taking you through my video presentation on the 3 VP tasks. Throughout the 3 VP tasks, I've had to explore and learn and apply the concepts and skills that I developed throughout this course. The analysis of interdeterminate structures involves calculating internal forces and moments in systems with more unknowns than equilibrium equations. Understanding this helped me predict how real-world beams and frames distribute loads more accurately than simple determinant models. And I'll be taking you through my presentation now. To kick things off, with VP Task 1, I was required to find a real-life scenario somewhere within my life to find a frame, a continuous beam with at least 2 spans, and a small truss. The 3 structures I found, one being at my friend's house, one being at a car park of a shopping center, and one being at a local school, really challenged me on the way I should think and analyze these structures that appear around me in my day-to-day life. And I found it very interesting, but also very challenging to find and look for such structures. In VP Task 2, the first question prompted me with a frame, which was undertaking 2 different types of loads. So as we can see at the top of the structure, there was a uniform distributed load with 93.8 kilonewtons, and that spanned over 4.25 meters. And we also saw a point load, which was acting from the right-hand structure, pointing to the left, at 1.9 meters from the bottom. In this question, I was required to find out what were the reaction forces utilizing the force method, as well as representing my findings in a shear force and bending moment diagram. To kick things off in this question, I solved the reaction forces at the 2 base points at A and D. And the way in which I did this was, initially I took the moment upon D, and by doing that, I was able to single out the vertical force at point D, and that hence gives the answer of 78.695 kilonewtons in the vertical direction. Then by having that, I was able to calculate the vertical reaction force at point A by summing all the forces in the vertical direction, and by doing that I singled out AY, and that gave me 319.955 kilonewtons. And then finally, to find the final reaction force was summing all the reactions in the horizontal direction, and that gave me negative 93.8 kilonewtons, which you see in the point D. Moving on from the initial calculations for the reaction forces, the next step required me to visualize the structure in the way I have in the right photograph in the slides. I had to take 5 different cuts at this frame and analyze the internal moment forces at each one. By doing this, I was able to calibrate the moment equations for each cut, and similarly, I had to also do this in a way which I have idealized the structure in a unit force manner. As you can see in the left photo, I had to make the vertical forces both 0 and made the horizontal forces 1, and again had to do 5 different cuts and find the 5 different equations to then be able to calculate the horizontal displacement of the primary structure at point A, and similarly I had to calculate the horizontal displacement of the vertical structure at point A as well. By doing this, I was able to get the final reaction forces at point A and point D. And here is a visual representation of the final calculations for the reactions. As we can see, there is 2 vertical forces acting at the 2 joints, so A and D. We've got 319.955 kilonewtons on the A, and at the D we have 78.695 kilonewtons occurring at D in the vertical direction, and then similarly we have 2 reactions in the horizontal, 82.717 at the A and 11.08 in the D. Utilizing the bending moment and the shear force equations, which were calibrated throughout the 5 cuts, I was able to visually represent the shear force diagram and the bending moment diagram. It is clear that the maximum shear force was 319.955 kilonewtons, and the maximum bending moment was 314.325 kilonewtons per meter. The second question of VP Task 2, we were challenged with a beam which had a distributed load and a point load acting as well. It also had a fixed support at the left side, and we also had a pin support at the right side, and at point B we also had a continuous type of support, so 3 different supports in this beam. And this question required us to use the slope and deflection method to calculate the moment at the supports, and also develop free body diagrams to help us represent the shear force and bending moment diagrams. The initial part of the calculations was to calculate the reaction forces. The way we did this was finding the moments between the 3 points, AB, BA, BC, CB, and by doing that, the reaction forces could have been calculated. Moving on, 3 cuts were done on the overall structure, one at the beginning in the between of point A and B, one just after point B, and then one after the point load. By doing this, we're able to calibrate 3 different moment and shear force equations, and that would assist us in visually representing the shear force and bending moment diagrams, as well as helping us find the maximum deflection, maximum bending moment, and maximum shear. After calibrating the 3 different equations for the shear and the bending moment, we're able to construct a shear force and bending moment diagram, and it is evident that the maximum positive shear was 89.05 kilonewtons, and the maximum in the negative direction was negative 173.59. Similarly, in the bending moment diagram, the maximum positive bending moment was 76.44 kilonewtons meters, and the maximum in the negative direction was negative 117.2 kilonewton meters. VP Task 3 had a question which had a fixed 2-pinned and 1 roller support with 3 different types of loads acting on it. My question was to figure out how to calculate the reaction forces on all 4, as well as calculating the bending and shear force diagrams. So the method that was used for this calculation for the reaction forces was the moment distribution table. This was used to find out the internal bending moments, as you can see represented in the 3 different cuts on the right hand side in the picture. And by using these forces, we were able to find the reaction forces. Furthermore, the method for the calculation of the shear force and bending moment equations was done by doing 5 different cuts on the structure, as you can see here. And by doing that, we were able to find each and every shear force and bending moment equation, which then translates to the formulation of the diagrams. After the calculation of the 5 different equations, I was able to construct the shear force and bending moment diagram. As we can see on the left-hand side here, the bending moment diagram, the maximum positive bending moment was 560.52 kilonewtons meters, and the maximum negative value for the bending moment is negative 622.067 kilonewtons meters. And if we move on to the shear force diagram, the maximum shear is quite evidently the 498.39 kilonewtons. And yeah. The second question in the VP Task 3 positioned us with a frame which had 3 different hinge points as well as 2 fixed supports at the ground. It also had a point load at the top left of the frame. This question asked to find the support moments at D and C, as well as finding the reactions at the supports A and B, and finally making a shear force and bending moment diagram. The method that was used for this calculation was initially splitting the frame into 4 different sections as where the hinges are, and each 4 sections idealizing it in different free body diagrams for the vertical and horizontal forces, and by doing that, able to calibrate the bending moments at each point as well as the internal forces at each hinge point. After the calibration of the bending moment and shears, we were able to construct a bending moment and shear force diagram with a maximum bending moment of 331.5 kilonewton meter and a maximum shear force of 209 kilonewton meters. Each of these methods that were described and utilized within VP Task 1, 2, and 3 were significant, as they were a great contribution towards understanding how a structure deals with load dependent on the different types of loads and different types of the structure condition. I found it easy to grasp how to do the moment distribution table, and I found it really hard to understand how to get the moment and shear equations when making a cut where there is a triangular distributed load. It made it really difficult figuring out how to use the similar triangles and etc. Thank you for listening.